In the next pair of questions on this Calculus 1 review, we're dealing with what we call related rates. And we studied these just before we got into the optimization unit in this class. And what we're investigating is how the change in one variable affects another. And in this particular example, we're told that the frequency f of a vibrating string is directly proportional to the square root of the tension, capital T, in that string. So frequency will change as the tension changes. And we go on to read that the tension of the string is going to increase at a rate of 2 newtons per second. So this is kind of interesting. We're increasing the tension T, so tension T is changing at a rate of 2 newtons per second. So that's a rate dt. Now it's a capital T for tension and lowercase t for time. So this value of 2 is equal to 2, is equal to our dt. So we would like to know at what rate is the frequency changing when the tension itself, T, is equal to 100 newtons. So what I'm going to do is I'm going to start with that function. I'm just going to rewrite it over here to give me a little bit more room to work. In fact, I'll give myself a little bit more space here as well. And what I'm going to do is I'm going to apply the derivative with respect to time to both sides of the equation. And so on the left side, the derivative of f with respect to t, we don't really know what that is, so I'm going to leave that as the differential df dt. On the right-hand side, we've got this constant 5 that can be factored out. And now I need to find the derivative with respect to time of the square root of t. Now I'm going to treat this as capital T, raised to the 1/2 power. And the derivative of t to the 1/2 power, well, I can use the power rule to determine that. And it's kind of a mini chain rule as well. We'll take 1/2 times t to the negative 1/2 power times dt. We have to account for this differential since the variables t are slightly different from one another. And again, I'm running out of room, so I'll try to pick this up over here. So that tells me that df dt is equal to 5 over 2. And this t to the negative 1/2 power is the same as the square root of t in the denominator of this fraction. So 5/2 from 5 times 1/2, and the negative power pushes the t to the denominator, and the fact that this is a 1/2 recreates the square root. And all of that, of course, is being multiplied by dt. And so our job is to calculate the rate of change in the frequency, df dt. This is the part that we don't know. When our tension is equal to 100 newtons, so our T value is 100. And don't forget that our change in tension with respect to time is being changed at 2 newtons per second. So we could use a calculator to simplify this if we needed to, or we might be able to get by without the use of a calculator here. These 2's will cancel. The square root of 100 is 10, so now we're dealing with 5 over 10, or in other words, 1/2. And our units here are fairly important. Frequency is hertz, so we're measuring this in 1/2 hertz, or I'm sorry, the rate of change is 1/2 hertz per second. And so it's important to note that at this specific moment, the frequency is changing at 1/2 of a hertz per second. But if the moment was different, say the tension was 200 newtons, well, we'll get a different rate of change of our frequency and a different value there. But at that specific moment, the two rates are related in this particular way. So in this next problem, we encounter an interesting phenomenon. We've got a cylindrically shaped elastic cord that has a particular volume of 500 pi cubic centimeters. So V is equal to 500 pi. When the cord is stretched, it maintains its cylindrical shape and does so in such a way that the volume remains constant. So our change in volume with respect to time is equal to 0 cubic centimeters per second. So that's important to note. The cord is stretched so that its height increases as a rate of, or at a rate of 5 centimeters per second. So the change in height with respect to time is equal to 5 centimeters per second. And our job is to calculate the time rate of change in the cord's radius. So at what rate is the radius changing? So dr dt with respect to time. So dr dt is what we're after here when the height or the length of this cord is specifically equal to 125 centimeters. So once it's stretched to 125 centimeters, at what rate is the radius changing? Now, we'll probably need to calculate the initial height, or we may have to calculate the initial height, but let's suppose that the height is currently less than 125. You could imagine that if the volume remains constant and we're stretching this cord in this direction, the radius itself must be decreasing. So I would expect to see some sort of negative value here. That's at least my preliminary guess. Let's see if our math supports that notion. Well, let's give ourselves some space and rewrite this problem. The volume is equal to pi, some constant, times radius squared times h. So pi times radius squared times h. And what we're doing is we're applying the differential with respect to time on both sides of the equation. So we'd like to see how the volume, the radius, and the height change per second. So on the left side, we have no real trouble here. We're going to note this differential as dv dt. On the right-hand side, we've got the number pi that acts as a constant. But now we're being asked to find the rate of change of r squared times h. And that's going to require the product rule. So our first function, r squared, and our second function, h. Now, the derivative of a product is the derivative of the first function times the second. So we want 2r dr dt. That's the derivative of r squared with respect to t. So the first function times the second function plus the first function, r squared, times the derivative of the second function. And again, we don't know the rate of change of h with respect to t, so we're listing that as the differential. And for as odd as this expression now looks, I think we're actually in pretty good shape because we actually have a lot of this information given to us already. For example, the volume does not change. dv dt remains at 0 centimeters cubed per second. Let's see, was there some other given information? The volume is currently 500, or I'm sorry, the volume of this cord is 500 pi cubic centimeters. So volume by itself is no longer part of this equation, but it certainly would be nice to know what the radius of the cord is originally, and also when the height is 125 centimeters. So maybe we don't need that originally, but at least when the height is 125, we would need to know the radius. Because I'm just going to leave this as an empty space right now. The radius is going to multiply by the rate of change of the radius, which we don't know. That's what we're actually looking for, dr dt, when height is 125 centimeters. And again, the radius squared, we don't know the radius at the moment, but the height is changing at 5 centimeters per second. So we've got 5 centimeters per second over here as our dh dt. And so if we knew what our radius was, then we can substitute those numbers into the parentheses here, and then we'd have everything that we need to isolate dr dt. The radius seems to be the hang-up at the moment. That's the only component that we're missing in order to allow us to solve for dr dt. So again, we're told that the volume of the elastic cord is 500 pi units. The volume formula is pi times radius squared times h. H in this case is 125 at this moment. So when we divide both sides by pi, that disappears. 500 divided by 125 is equal to r squared. So we now have 4 equals r squared. That means that the radius of this elastic cord is either 2 or -2. And of course, we can't have a radius of a negative measurement, so we're going to say that the radius is equal to 2 centimeters. Now, it may be worthwhile to combine like terms and simplify a little bit. So I'm going to note that the dv/dt is still 0. We've got pi, and now 2 times 2 times 125. So that's 500. And our units there are centimeters squared, because we have 4 centimeters times 125 centimeters. That's 500 centimeters squared times dr dt plus 4 centimeters squared times 5 centimeters per second. So that's going to be 4 times 5. That's 20 centimeters cubed per second as far as our units go. And now we can go after dr dt. We can divide both sides by pi, which effectively does nothing. 0 divided by pi is still 0. Then we could subtract our 20 cubic centimeters per second. So now we're dealing with -20 cubic centimeters per second equals 500 centimeters squared times dr dt. And so if we're trying to isolate dr dt, we can now divide both sides by 500 centimeters squared. And -20 divided by 500 is going to be some decimal that we can reduce. And centimeters cubed per second divided by centimeters squared leaves us with a unit of centimeters per second, because the cube can be reduced by a factor of 2. And so now we're looking at a rate of change of -20 over 500 centimeters per second, dr dt, the change in radius with respect to time. And that simplifies to -1/25 centimeter per second is our rate of change of the radius with respect to time. And here again, that's the change in radius with respect to time at that particular instant. You can imagine that the radius decreases pretty quickly as we start to stretch this elastic, but as we have this elastic cylinder or cord, if you want to think of it that way, once it's really long and narrow, its radius doesn't change nearly as much, or at least not nearly as fast. So at this particular moment, it's changing at a rate of -1/25 centimeters per second. We have one more related rates problem before we get into an optimization series of questions. So let's talk about this related rates, and we'll probably stop this video after that. We've got 2 cars that are moving in different directions. One is moving to the right away from an intersection. One is moving up towards the intersection. And we would like to know the rate of change in the distance between the 2 cars at the moment that x is equal to 40. So we've got x equal to 40, and when y is equal to 30. Now, for reference here, the change in x with respect to time is equal to +15, and these are meters and meters per second, whereas dy, the change in y with respect to time, is going to be considered a -10 meters per second, because the distance of this car from the intersection is actually decreasing at 10 units, or 10 meters per second. whereas up here it's increasing at 15 meters per second. So that's good to know. Now, the distance between those two cars is simply the length across the hypotenuse of that right triangle. So distance squared is going to be equal to x squared plus y squared. So it stands to reason that after we apply the derivative with respect to time on both sides of the equation, and essentially to all terms in this equation, then the derivative of d squared with respect to time is going to be 2d dt, and that's equal to 2x dx dt plus 2y dy dt. And based on the given information, we should be able to substitute for 5 of these 6 unknown values, and that'll allow us to compute the final missing value. So we're looking for the rate of change of d with respect to time. We have x dx dt, we have y and dy dt. What we don't have right now is our current distance. But that's actually pretty easy to compute because, again, d squared is equal to x squared, which in this case is 30 meters, and sum to that y squared, which is 40 meters. So d by itself is the square root of 30 squared plus 40 squared meters. And that's a nice 3, 4, 5 triangle. So the distance at this particular moment is precisely 50 meters. So as it turns out, we do have 5 of the 6 components. We have 2 times 50 meters times dd dt equals 2 times 30 meters. Oops, sorry, 40 meters. Sorry, our x value was 40 and our y value was 30. That doesn't change our distance. So 40 meters times the rate of change is positive 15 meters per second plus 2 times 30 meters times our rate of change there, which is negative 10 meters per second. And I think it's a good idea to report our units because that'll help us calculate our result and verify that our solution is meaningful. You know, for example, when we multiply these 3 terms together, our calculated result is going to be meters squared per second. And then this one also is meters squared per second. And then after we divide by 2 times 50 meters, well, that unit meter will cancel or reduce one of the factors of meters here, and we'll be left with meters per second, which is the rate of change that we're after. So this side of the equation does come out to be 600 meters squared per second. So this this expression plus this expression is 600 meters squared. We're going to divide that by 100 meters because that's the product that we have over here. And we can now claim that the rate at which the distance is changing here between these two cars is 6 meters per second at that precise moment. So I think that's a good stopping point for this video, and I think with one more video we'll be able to finish up this review. Thanks for watching.